So when we talk about levers, we talk about wheel and axle. What we're going to be doing, like I said, I'm going to be focusing on levers just for the beginning part of it, chatting about that, and then also mainly focusing on wheel and axle. The nice thing about wheel and axle is if you're fairly confident in levers, then you'll be fairly confident in wheel and axle. It's very similar. Okay, just as a quick recap, I guess I should say. I sent out an announcement to you guys yesterday as just kind of like a, hey, this is what you need to do before you walk in. Here's your homework that I'm going to assign to you, so on and so forth. Do yourself a favor. If you did not have that practice set of questions done, or at least started or worked on maybe once, do yourself a favor and just try to keep on top of your stuff. Because one of the things that I run into, and I'll give you an example. So yesterday, I had my other classes, right? I had my 8-day classes, and I have a couple of POE classes on that day. And when I went back to see how many people had done those, like that practice set of questions, I was amazed to find out that about 30% of the classes had even done them, even once, right? Which is, was a concern to me. And that's one of the reasons why I sent you guys the email, just as a reminder, like, hey, if you haven't done it, you want to do it, check it out, because it'll help you out. And, even still, I'm looking at, there's only about 30% of you that have done those, okay? So if you have not done those, that homework that I gave you, it is important for you to do that kind of stuff, okay? What I want you to realize is the beginning of the year, when I say, what do we heard about POE, there are some students that say, oh, I heard it was super hard and it's impossible or whatever. Well, I get that what we just did maybe in levers was maybe fairly easy to you and you didn't really feel like you needed to go through it. But if you walked out of last class saying to yourself, yeah, I still have some questions and I'm not great at what he went through, then you should definitely be looking over and trying to get yourself ready, okay? Because over the last day or two, I haven't really had anybody come in for flex time for POE, right? I had one student who, he came in, he popped in, he asked a question, it was a great question, and he jetted out, which is fine, right? He was working on the practice, awesome, okay? But you can't wait until I give you an assessment to realize that you don't know what you're doing, right? If there's a question mark above your head, when you walk out of class, you need to ask questions. You need to get help, okay? Don't wait until you get the grade to realize, oh, wow, I didn't know what I was doing, right? Like, if I were to say to you right now, hey, you guys are going to take a quiz today. If that phrase right now gives you fear and worry, right? And you didn't go through that practice, that's what I'm talking about. Okay? All right? You guys understand what I mean with that? All right? So if you're walking out and you feel like you could probably use some help, right? First of all, that homework is helpful because it asks you to go through a couple things, right? It asks you to go through and check it, and it gives you the opportunity, really, to be able to go through some of the questions that I would be assessing you on. So again, one of the biggest things that people do, and it takes them a little bit to figure it out, is they wait to get help. And when they wait to get help, by the time you're getting help, then now you're behind. Okay? And they think, I make kind of the joke that, I've asked people in the last couple years, I say, how many people felt like they did a lot of homework in middle school? And there's maybe one person that just kind of like slowly puts up their hand. But then I've had quite a few people that kind of giggled and said, homework? I didn't do any homework in middle school. I did very little. And I did well, kind of thing. Right? So just do yourself a favor. Don't wait. Right? And make sure you're doing your homework. Okay? The homework that I'm going to give you is not excessive homework. It's not asking you to do a ton. Okay? For instance, the homework I'm giving you tonight, I'm asking you to go through 3 questions twice. Right? At the minimum. So if you feel like after those 2 rounds of 3 questions, you feel like you're good, great. Move on, you're done your homework. Don't worry about it. But if you feel like, I could probably use a couple more, just do it a couple more times and see where we're at. Okay? All right. So what I have open is I have open the PowerPoint from the module that you guys use to fill out your essential questions. Okay? So I have out this PowerPoint. And again, we're just going to do kind of a recap, right? So mechanical advantage, we're going to mainly talk about this right here. Okay? And again, we've kind of mentioned this, but I just want to reiterate. So if mechanical advantage is greater than 1, it means it's less effort force, but you have to go greater distance. So what does that mean? That means less effort means it's easier. Greater distance means you got to go further. So it's a give and take situation. It gets easier if it's greater than 1. It gets easier, but you have to go further. And I'll give you a great example today about it, and you'll understand what I mean. If it's less than 1, you go less distance, so it gets easier in distance, right? You go less distance, but you have to go. It gets harder in force, but you have to go less distance, right? So it gets easier in distance, harder in force. Okay? Right? So if it's greater than 1, it's easier in force and weight. If it's less than 1, it's easier in distance. And again, it's a give and take situation. And if you don't have some of these notes, maybe in your notebook or in those essential questions, just make sure you get them down. Okay? So we talked about IMA, we talked about AMA last class. We are going to use them again today, right? We talked about first class levers and second class levers. Okay? So make sure you review this if you don't understand these things. Okay? But I want to talk about moment. All right? And I'm going to show you how smart you guys are already. Okay? Because I think it's pretty cool that when I ask you at the beginning of the year, before we even do POE, right? Literally first day, I ask students, and I give them this example, and I think it's a great example. I say to them, you're on the playground, and there's a seesaw, and there's a kid who doesn't weigh very much, and then there's a kid who weighs a lot more, right? And I ask you as a group, what do you do if I asked you to put those kids into like a balance, right? I want you to make them balanced. Most people will say, well, either make the lighter kid heavier, which we can't do. We can't shove cheeseburgers down his throat. That doesn't work, right? We can't hand him a bag of candy and say, here, eat 50 pounds of candy for us, right? That just doesn't work like that. Somebody might say, well, we can change the seesaw. And I say, it's a seesaw. We can't change it. Not like we're going to take it apart and start cutting on it. It's not our seesaw. But some people say, just take the heavy kid and move him closer to the fulcrum. And that'll make it more even, and make it more what we call static equilibrium. Make it more in a balance. Okay? And I think it's awesome that we, even before we talk about POE, can at least get that basic concept, right? We kind of inherently know that because we've lived in the world, which is awesome. But why does that work, right? We didn't make the heavier kid lighter or anything like that. What happens is what you're playing with is this thing called moment, right? And if you're not writing it down, you probably want to jot this stuff down as we're going, right? So when you move that kid, you're playing with their moment. And what a moment is it's what we call the turning effect. It's like the effect that those kids have in rotation. Right? And some people will say, like, yeah, the light kid out here, right? The kid that's way out here on the end, because they're further away, has more leverage. Because they're further away, right? Well, that leverage is essentially what that moment is. Okay. So when we look at the formula to the right, it says moment equals force times distance. Now take a look. Right? If I move the heavy kid way out there, right? This light kid has a small amount of force, and they have this distance. So they have this force and this distance. This kid over here has their force and their distance. And those two things, these two combine together, make a moment, which makes this want to spin this way. And these two over here make this want to spin this way. And when we want them to even out, that's where you tell me to do this. You tell me that the light kid can stay where they are, and the heavy kid, we're going to bring it in closer. Because what have we just done? What have we just changed? What have we just manipulated? When we move them, go, just unmute yourself and you can answer. All right, we changed the moment of the heavier kid. We changed the distance. We made the distance smaller. And that distance, because that distance got smaller, our moment got smaller. Right? Our moment got smaller. Okay. So I'll put some numbers to it just so you guys can see it. And I won't erase this yet because I know some of you are still writing. Let's just say, I'm going to move it down just to give us some room. Let's just say the light kid over here weighs 50 pounds. And the heavy kid over here weighs 100 pounds. In order for those things to work, and let's just say this light kid is, I don't know, sitting 10 feet from the middle of that seesaw, from that fulcrum. Well, when you do 50 times 10, right? If you do force times distance over here, so 50 times 10, we get 500, right? 50 times 10, pound-foot. And it wants to spin this way. It wants to spin counterclockwise. How far do we have to make the 100 in order to counteract? Go ahead, just unmute yourself, whoever. Right, so 5 feet, right? So this person has to sit 5 feet from that fulcrum. And you might be saying to yourself, whoa, hang on a second. How the heck did they figure that out? Well, they probably figured out by saying, well, if it's 500 over here, what times 100 equals 500? Right? What times 100 equals 500? And maybe, just maybe, somebody else looked at it like this. Well, if this and if these two numbers, if this is twice as heavy as this, that means that this distance has to be twice as long as that. Maybe you looked at it like that. Okay? The point is, though, you kind of get what we're talking about, right? I've just proven to you that, yeah, even before class, we started this whole journey in POE. You knew what a moment was. You just didn't know what it was called, and you didn't know what the formula looked like. you kind of inherently knew that stuff already. Okay? I'm very confident that if I gave every single one of you the opportunity individually, and I had a light kid and a heavy kid on either side of that seesaw, and I said, I want you to put them in the balance, all of you, given a little bit of time, some of you might be a little bit faster than others, which is fine, but you'd be able to figure it out. Even if you're just playing with it, you'd be able to just kind of balance it. Okay? Well, we can do it in numbers. If you can do it trial and error, we can do it in numbers and actually hit it spot on right from the beginning. Okay? All right. So, let me show you wheel and axle. Because I just said that levers and wheel and axle are very similar. So, what you're going to do is you're going to draw a wheel and axle. And that's how we draw a wheel and axle. So the outside ring is a wheel. The inside ring is the axle. So you're going to draw two of them. And in a wheel and axle, there's a second and a third class wheel and axle. Just like levers, where levers there's a first, second, and third, in a wheel and axle, there's only second and third. And you'll kind of see why. So let me show you where the lever exists, and that will kind of help you. So if I put the fulcrum, think about what a fulcrum is. Fulcrum is where things spin around, right? So that fulcrum, the point of that fulcrum is right in the center of these two. And there's a lever that extends out from them. Now, just like a second class lever, a second class wheel and axle has the effort on the outside. It has the effort on the wheel. And the resistance is on the axle. And I bet you can guess what the second or the third class is, right? Instead of the resistance being on the inside, resistance is on the outside, just like that third class lever. And I'll give you a minute to kind of jot that down. And then we'll talk about some examples, and it'll hopefully start to tie things together. If you're still a little cloudy, probably start to tie things together. So look around your room. And I think this is awesome, right? I mean, virtual learning is not the greatest successes that we can ever think of, but normally we're sitting in the same room, so we're looking at the same stuff, right? You're all in different rooms, so you have all different things that you're looking at, right? And if you can type in the chat for me, what kind of examples are there of a wheel and axle, and if it's second and third class? All right, so we got a doorknob. The first one we got, doorknob. And a doorknob is going to be a second. Doorknob is going to be a second. Think about the way a doorknob. I'm just going to put knob because essentially all knobs work the same, right? So that could be a doorknob. It could be a garden hose knob, or what we call a spigot, right? Think about it. You turn the outside of that wheel, and it turns the inner wheel. The scroller on a mouse. I have never heard that before. See? A scroller on a mouse. Yeah, second class lever. Second class wheel and axle. All right, let's talk about a fan. So a fan is interesting. So is a fan, think about the way a fan works. Do the blades power the fan? Do the blades power the axle, or does the axle power the blades? Right, the axle powers the blades. So because the axle powers the blades, a fan is a third. It's a third class wheel and axle. So sticking on that fan conversation, how about a windmill? Is a windmill, is it a second or is it a third? Right, it's a second because the blades are moving the axle. So let's talk about, there was some of the other ones that, so a wheel on a car. All right, so let's be very descriptive on a car because there's a lot of wheels, right? And I don't mean like there's 4 wheels. I mean there's a lot of wheel and axles. Okay, so let's talk about like the tires on a car, right? Tires on a car. Tires on a car are turned. Are they turned by the road, or are they turned by the engine, which is connected to the axle? Right, the engine is turning that. So that means that the tires on a car, or the tires on a bike, same thing, right? Tires on a car are third class because the engine spins the axle then spins the wheel. And the reason I'm being kind of specific about that is, what if we said a steering wheel of a car? Let's think of a steering wheel. Steering wheel, you turn the outside, right? So steering wheel is going to be a second. Yeah. So steering wheel. And there are a ton more. I mean, there's hundreds and thousands of more, right? Those are like the major ones that we just kind of chatted about, right? The point is, if you put some critical thinking into how that wheel works, you can figure out if it's a second and a third class, right? Now, think of what a steering wheel is supposed to do. Steering wheel is supposed to make it easier to turn, right? Okay? And I told you this from the beginning, and I'm going to say it again. I apologize because you're never going to look at the world the same ever again, right? We've talked about walking through the threshold of a big building and so on and so forth, and all, putting a lot of trust in the engineers. So you've probably all been on a school bus, whether it is you take the bus or you've gone on a field trip. You've seen the inside of a school bus before. And if you haven't, maybe you've seen the inside of a fire truck or a tractor trailer, whatever. Okay? Why in the heck are the steering wheels so big? Say again? Right, like everything is heavier. Right? The school bus, the fire truck, the tractor trailer, those are all heavy items, right? Okay? So that's why that steering wheel is bigger. You probably have never thought, most people, it's not something you walk into a school bus and go, hey, that's a pretty big wheel. I wonder why it is. You just, hey, it's a big wheel, and you just keep on moving, right? You never thought about it, right? And it's not, that wheel is not just big, and this was what, like if I asked my, if you asked an elementary school kid, why is that wheel big? They would say, well, because the bus is big, so they want to make it big because everything's big. No, it's big because it's heavy, right? And they have to make it easier for that person to turn it, right? So it's a conversation that you definitely have to think about, right? Could you put a small wheel on a school bus? Sure, you could, right? It would make it harder to turn. The bigger the wheel, the easier it is to turn. Now, with that steering wheel, though, because it's so big, you're giving up something, right? You're getting force, it's making it easier, but you're giving up distance. We just talked about that. So think about this. You ever try to watch, you ever seen a school bus driver try to go around a sharp corner reasonably quickly? What does it look like? Yeah, it's like a fiasco of hand movements. I mean, they're like trying to turn that wheel as fast as possible. Their hands are going, and it just feels like that wheel just keeps turning, right? They're giving up all of that distance to be able to make it easier, right? If you've ever seen the inside of a race car or a go-kart, like an F1 or like a Formula One or Indy car or any of those things, right? Those wheels are tiny. I mean, they are tiny. They're maybe 8 inches across. Why? Because those cars are so light that they don't need all that extra mechanical advantage. But also, when you're racing and you're going around a corner, you want to be able to turn what they call lock to lock, which goes from one side to the other very quickly, right? My hands, if that wheel is this big, my hands, in order to go from full lock left to full lock right, I only have to do this. That's it. My hands can just do that. If I have a big steering wheel, my hands literally have to do this, and then they have to do this, right? Like, that's a lot. I'm giving up that distance to make it easier in force, right? So keep that in mind, right? Again, you probably never thought about that, you know. And there was some conversation. So yes, so those pieces of equipment, so cars, fire trucks, all those things, school buses, they all have a power steering, which is a system that is basically, it's a hydraulic system, and it allows it to also increase your force. Yes, so we could make that power system stronger, power steering system stronger, absolutely. Okay. But you never probably thought about why that wheel is so big. You probably recognize that it's big, but you never really gave it any thought as to why, right? That's why. Because it's so heavy. And they have to be able to turn. Right? But as a designer, you have to think about that kind of stuff. So, let me show you a math example of how this works. Okay? We're going to use that steering wheel as an example. So let's say that the outside of that steering wheel is, I don't know, we'll just say 18 inches in diameter. And just so you're clear, that symbol, I'll write it down for you, stands for diameter. The line goes through both sides of that circle. That symbol stands for diameter. Okay? So the size of that wheel is 18 inches in diameter. And let's just say the size of the axle is, I don't know, 2 inches in diameter. And let's say that school bus driver can exert, I don't know, 15 pounds of effort out there, right? So this is a steering wheel. So what I want to know is, what is the IMA and what is FR? Now, you have never done a problem like this, right? Pretty sure nobody in here is a POE expert, or maybe you are. Maybe you thought about it. Okay. So use that guess method. I'm going to show you that guess method here in a second, right? So let's use that guess method. And if you just want to type the answers in the chat, that's cool. That works. What are we given? What are some of the givens Anything with a number on it. What are we given? Okay, so which one is which? And when I say which one is which, like which one is which one is DE and which one is DR? Okay, so the DE would be the 18 inches in diameter, and the DR would be the 2 inches in diameter. And the reason that we know that is because if this is a steering wheel, your effort is on the outside. So this 15 pounds is also your FE, right? So we have steering wheel, your FE is on the outside, which means your DE is on the outside, which means your DR is in the middle. So go ahead and just jot them down. So we have FE has 15 pounds. We have DE, which is 18 inches diameter, and we have DR as 2 inches in diameter. Our unknowns, remember I'm asking you for IMA and FR. Now, the equation, think about the equations that we have or what we need. Well, we know the IMA equation, right? IMA equals, I'm a deer, so DE over DR. How about this FR? How can we find the FR? Exactly, we can use that static equilibrium equation that we learned last class. So we can use that FE times that DE equals FR times DR. And I'm just going to do these two problems side by side, right? So I'm just going to do this. So, and this is my substitution and solving. So IMA equals DE, which is 18 inches over 2 inches. So IMA, 18 divided by 2, 9. Okay. So that means it's the mechanical advantage of 9, which means it's 9 times easier in force. But you got to go 9 times further. Let's try this FR equation. So we have, and I'll write the equation because it's kind of long. So we have 15 pounds, 18 inches. So this is where having a calculator helps a little bit. So 15 times 18, we get 270. And those units come along. So it'll be pound inches. The right side we can't do anything with yet. We need to get rid of the 2 inches over on the right. So we're going to divide both sides by 2 inches. Inches cancel, so 270 divided by 2 is 135 pounds is your FR. So you could overcome 135 pounds. You could exert 135 pounds by only using 15 pounds of force. So that school bus driver, that retired school bus driver only has to exert 15 pounds of force in order to actually make 135 pounds of force, right? I want to point something out, okay? And I'm going to give you a minute. I see a couple heads down because we're writing, which is good. So I'm gonna kind of slow down for a minute. But I'm gonna point something out. So, what do you notice about the 18 inches here and the 2 inches here? So obviously 18 is 9 times the size, right? 18 is 9 times the size of 2. That's where our mechanical advantage is. What do you notice about the fifth? Oh boy, that's not going to work. Let's try that again. Let's try blue. What do we notice about 15 versus 135? Yeah. Right. Or you could say 135 is 9 times the size of 15. Right? So it's a multiplier. That 9 that we calculate, that mechanical advantage, is a multiplier. Right? It either makes your distance 9 times more, or your force 9 times more, depending on which way it's going, right? Now, one thing I want to point out, and nobody asked the question, which is it's a pretty normal thing, right? So don't take it the wrong way. I'm not giving you guys a hard time. This is the first time we've ever had to deal with diameter, right? Because we're dealing with wheels. In circles, we have to deal with diameter. The problem with wheels and diameter and that kind of stuff is there's 2 different dimensions. There's really 3 different dimensions of a circle. There's diameter, there's radius, and there's circumference. Okay? Here's the point that I'm going to make to you. And that is, you notice how that is a diameter and that is a diameter. Right? They're the same. We didn't have to do anything. If they're the same, you can use them in all of your equations. So what am I saying? I'm saying that if this was radius and this was radius, you could just use the radiuses, as long as they're the same. Okay? What you couldn't do, though, is you couldn't have one of these be radius and one of these be diameter and throw them into your formula, because it doesn't work. You have to convert one. You have to convert them to be the same. Okay? All right? It's kind of like the same thing. Like if this said inches and this said feet, you can't multiply feet and inches. It just doesn't work. Right? Like, we understand that, right? So it's the same thing. Just make sure that they are the same. If it's diameter, use diameters. If it's radiuses, use radiuses. Okay? Just make sure they're the same. Oh, good. Question. Yep. So the question was, if it's radius, would you just double the would you double the radius to get diameter? And yes, absolutely. Or you could take the diameter and cut it in half. Yeah, either one would be perfectly fine. Just as long as you're putting in the same type of dimension into the equation. Yeah. Okay? You could, yep. So that's a great question. If you're dealing with circumferences and that kind of stuff, we deal with everything in decimals in this class. So never leave it in like a pi format. Always just find the actual value and just use the decimal number. Yeah, like 3.14. Yep. I mean, if you just have a regular calculator that doesn't have a pi button, I just tell people to use 3.14, and that's perfectly fine. Yep. And that's a great question. It's a great segue, because I got one more thing to mention. It's not anything crazy, not super difficult. So if I'm rolling a wheel, right? If I roll a wheel along the ground, okay? if I roll this wheel 1 revolution, how far does that wheel roll? Right, because you're rolling along the outside of the wheel. I always ask people. Some people say that's like the way that I'll kind of I'll progress them if they're not getting it is I'll say what part of the wheel do we roll along, and they look at me like, what kind of question is that? Like the outside, duh. Yeah, so I will ask them. I'll say, right, the outside of a wheel. What is the outside measurement of a wheel called? What's the outside measurement of a circle called? And that's the circumference. Okay, so if I asked you, so I'll just give you an example. If I said this wheel was 20 inches in diameter, and I asked you how far it would roll in 1 revolution, the answer is not 20. The answer is the circumference of a 20-inch wheel. And if you're curious to know how to find circumference, it's pi times d. So you would do 20 times 3.14, 20 times 3.14, and we'd get about 62.8 inches in 1 revolution. How would I handle the problem if I said 4 revolutions? Right, I would take this circumference and multiply it by 4 to get my answer. Okay?